In this video, we'll be finding the derivative. For a function f of x, the derivative at a point x sub 0 is the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 all over h. So there are some notations for the derivative. There's actually several notations for the derivative. We have the prime notation here. That little like tick mark is called a prime, so you might hear this said, y prime or f prime of x. This notation was developed by Newton, but then there's this other notation that was developed by Leibniz. See, calculus started being developed in the late 1600s, and Leibniz was in Germany and Newton was in England, and they actually both started developing calculus at about the same time without ever consulting with each other. Leibniz was the first to publish his paper, although Newton actually started on the work earlier, so there has been a debate through all the history of math and calculus for the last 400 years on who actually developed calculus. But because both these men developed this idea at the same time, but independent of each other, they both developed different notation, and both notations have stuck today. I usually use Newton's notation most of the time just because it's flat out less to write, but as you get higher into calculus and do more complicated things like differential equations, then Leibniz notation becomes the one that you want to use, but you should be comfortable with them used interchangeably. So for Newton's, like I said, we call it prime, so f prime of x or y prime. And for Leibniz, we actually say, df dt, or I'm sorry, df dx, it's the derivative of f with respect to x. And sometimes you'll even see it like d dx of with or without the f of x. And these over here, you won't see those until you're pretty high up in your calculus sequence. But different notation, we definitely need to be comfortable with the first four and even the ddx of f of x. All right, so beyond the history of our notation here, if f prime of x exists at a particular x, we say f of x is differentiable at x. So being differentiable simply means that it has a derivative. If f prime of x exists at every point in the domain of a function f of x, we call the function f of x itself differentiable. So we can be differentiable at a particular x value, a particular point, or the entire function itself can be differentiable. If a function f of x is differentiable at every point on an interval, the derivative itself is a function. And that derivative, that's why we're using function notation for our derivative, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the same definition for derivative that we've been using. We've just dropped the sub-zero because we're not going to be looking at a particular x value. Here, we're being more general in speaking about the derivative being a function itself and the derivative of an entire function and not just at a particular x value. So let us find the derivative of each function. And we're going to be using that limit as as h approaches 0 of f of x plus h minus f of x all over h. And since they gave us y, we're going to say y prime equals, or you could have said dy dx if you wanted to use Leibniz notation. Okay, well, let's plug in. This is equal to the limit as h approaches 0 of 1 over 3 times x plus h minus 1 over 3 times x all over h. We certainly can't plug 0 in for h now because we'll get something that's undefined, so we want to simplify this complex fraction by multiplying each term by the LCD of all of our fractions, which is 3x times x plus h. Our denominators cancel. In the numerator, we're left with x minus 1 times x plus h. So that's a limit as h approaches 0 of x minus 1 times x plus h all over. Now in the denominator, I don't want to multiply this out because we're going to want to cancel a factor of h ultimately, so we want to leave it in factored form. I'm going to write this 3xh times x plus h. Distributing our negative in the numerator, it's going to be x minus h all over 3xh times x plus h equal to the limit as h approaches 0. In the numerator, our x's are going to fall out when we combine our like terms, leaving us with negative h over 3xh times x plus h. Our denominator is in factored form, and we have a single term in the numerator, so we can now cancel our h's out. This gives us the limit as h approaches 0 of negative 1 over 3x times x plus h. And now it's safe for us to plug 0 in for h. We end up with y prime being equal to negative 1 over 3x squared. Let's try another one. This time f of x equals the square root of x minus 1. F prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. This will be the limit as h approaches 0 of the square root of x plus h minus 1 minus the square root of x minus 1 all over h. We can't plug 0 in for h now because of that factor in the denominator. So we want to simplify this. And the way that we're going to simplify this is by rationalizing the numerator. We're going to multiply top and bottom by the square root of x plus h minus 1 plus the square root of x minus 1. We saw this technique when we've covered difference quotient in the past. We get the limit as h approaches 0. Now in the numerator, because we have conjugates, we can multiply just the first two and the last two together. Doing that will leave us with x plus h minus 1. Now we're going to have minus the result of multiplying square root of x minus 1 times square root of x minus 1. So be sure to put that x minus 1 in parentheses. And my denominator I'm going to leave in factored form. Let's simplify the numerator, distributing our negative and combining like terms. Like terms in the numerator, x's to combine, and they'll fall out. Constants to combine as well, and they also fall out. So this gives us the limit as h approaches 0 of h over h times the square root of x plus h minus 1 plus the square root of x minus 1. And we can cancel these h's out. This gives us the limit as h approaches 0 of 1 over the square root of x plus h minus 1 plus the square root of x minus 1. Now that we've eliminated that factor of h in the denominator, we can plug 0 in for h. So it'll be 1 over the square root of x plus 0 minus 1 plus the square root of x minus 1. So it'll be 1 over the square root of x minus 1 plus another square root of x minus 1. We can combine those like radicals in the denominator, giving us f prime of x equal to 1 over 2 times the square root of x minus 1. In our next example, f of x is a piecewise function, 2x when x is greater than or equal to 1, and 2 when x is strictly less than 1. And we want to find f prime of x of 1. Because we have a piecewise function here, we want to find the derivative at the specific point. We're going to be looking to find the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Something else to note here, f of x plus h takes on a different value depending on whether h is positive or negative. And that's because the derivative, the point we're finding the derivative at, is the spot where our piecewise function splits. So because of this, we must find the limit as h approaches 0 from the left and as h approaches 0 from the right, because we're going to use a different function depending on it. All right, let's start with finding the limit as h approaches 0 from the left. Well, if we're approaching 0 from the left, that means h is a negative number, so f of 1 plus h is actually an x value less than 1. So we're going to be using this function when x is less than 1. So this is the limit as h approaches 0 from the left of 2 minus, now f of 1, we're going to be using the other function for. So we use the bottom function for finding f of 1 plus h, but we're going to be using the top function for finding f of 1 because we use the top function when x is equal to 1. So 2, and then plugging 1 in, that's going to be 2 times 1 all over h. Now this is the limit as h approaches 0 from the left of 2 minus 2 over h. So that's the limit as h approaches 0 from the left of 0 divided by h. Now, frequently we'll just say, oh, okay, I'm just going to plug 0 in for h because it doesn't create something that's undefined. Well, here it would if we just plugged in h. But remember, we're approaching h from 0 from the left side, so really what this ends up being is 0 divided by a super small negative number. We're not actually dividing by 0, so 0 divided by a super small negative number is equal to 0. So now let's find the limit as h approaches 0 from the right side. Well, here, because we're approaching the right side of 0, our h value is actually a positive number. So when I do 1 plus this positive number h, I'm greater than 1. So this time, when we're finding f of x plus 1, we're going to be using our top function because x is greater than 1, and we'll also be using the top function for finding f of 1. This is the limit as h approaches 0 from the right of 2 times 1 plus h minus 2 times 1 all over h. That's the limit as h approaches 0 from the right of 2 plus 2h minus 2 all over h. We'll combine our like terms in the numerator. The limit as h approaches 0 from the right, our 2's are going to fall out. That's 2h over h. And then we can simplify our h's. We get the limit as h approaches 0 from the right of 2. And we know that the limit of a constant is always equal to that constant. So we got a limit of 2 for our right side and a limit of 0 for our left side. Since the left-hand limit and right-hand limit don't match, we can conclude that the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h does not exist. Therefore, our function f of x is not differentiable at x equals 1. So since we couldn't actually find the limit, that means that it's not differentiable. And if we took a look at the graph there, we would see that it was discontinuous, and it's not going to be differentiable where it is not continuous.